Hello and welcome. In this problem, we are going to illustrate the use of several test steps using different model. The IG model, the binary mixture IG plus IG model, and the NIG model where we can treat a general mixture, and finally the IGE model where we allow reactions to occur. Well, it may sound very complicated, but let's get started. Well, just the background for this you will find in chapter 11 and 14 where mixtures are treated. Again, the IG model should be very familiar to everybody. And then we'll treat air as a mixture of oxygen and nitrogen using the binary mixture model. And then we'll use the generalized mixture model where you can have as many components as you like in a gas mixture, but we'll still use air as our in this example. And finally, the chemical equilibrium model where oxygen and nitrogen can react at this high temperature of the problem, producing NOx. And we'll also have a chance to see the composition of NOx using the IgG model. So let's get started. Well, this is the previous problem I was solving. Okay, let's go to the system state test calc. I'm already logged in and launch the IG model first. HTML5 page, and we are in. Air is the default fluid already, as you can see, 100 kPa. 300 Kelvin is our initial state, and I think it was given that we have 10 kg of air. So state 1 is very straightforward. And the final state also, all the data is given to us. So we have, we don't know the pressure, I'm sorry, but we do know the temperature is given as 3000 Kelvin. Let's make sure the temperature given is 3500 Kelvin. And of course the mass of the mixture is not changing. Mass must be conserved, and it's a rigid tank, so we'll assume the tank never changes its volume, and we get the final pressure, which is 1167 kPa. If you want to know how much heat is transferred, we can simply go to the IO panel, and the heat transfer Q will be equals what? Mass is mass, which doesn't change, times energy at state 2 minus energy at state 1. You can use the energy equation to show that this is the formula for heat transfer because there is no boundary work. So this is in kilojoules. So it's about 28.843 million joules. So let's write down what we are getting, the answers. So the first one we get is that the ideal gas model gives us the final pressure was how much? 1166. And heat transfer we calculated to be 28.843. So many million joule. Okay, let's go use the binary mixture model IG. Okay, so we can start a different test call this time. We go again to the system states and we look for the IG plus IG model, which is right here. We launch it by going to the HTML5 page. So this time we are going to treat air as a mixture of oxygen and nitrogen. So we pick those gases here. And how do you constitute air here? Oxygen, the mole fraction of oxygen is given to us, 21%. So it's 0. Volume and mole fractions are equal in an ideal gas mixture. So therefore, if I specify Y of A, the Y being the mole fraction, as you move the pointer over, you will notice is mole fraction. So it's 0.21. And oxygen is 0.21, so obviously nitrogen will be the rest because it's a binary mixture. So this constitutes what I'll call air. And for state 1, it's given 100 kPa and 300 Kelvin. and we have 10 kg of that, right? So state 1 is completely known. For state 2, again, air is not changing, it's still 0. We can write equals YA1. We could also type in 0.21. Temperature is 3500 Kelvin. And of course, mass doesn't change, equals M1, and volume doesn't change, Vol1. Now we calculated the state. Notice the pressure is exactly the same, 1167. So let's fill up this table, 1166 kPa. And what is Q? We can do the same thing here. Q equals M1 star E2 minus E1. There's no reason for the answer to change much because, which is 29.8, it slightly changed, and the reason being, in this case, air is treated as a gas with a different molar mass. It has some little bit of CO2, whereas in this IGE model, we're just treating air as just a mixture of oxygen and nitrogen. That explains the slight difference in the answer. Okay, let's go to the NIG model, and the answer should be same as the binary mixture model, but I'm doing it here just to illustrate how to use that model. So again, we go to the system state and launch right here the NIG model. And it has a completely different look, but it's a very versatile test step. So mixture A, let's define it as, so we want to define air. Well, we can just click on air, and if I say I have 10 kg of air, it will immediately populate, or any amount of air if you put, and click add. Notice what happens. Air is split into oxygen and nitrogen. Another way to do it is that, okay, let's take them out, remove this. If you want to treat air as a mixture of oxygen and nitrogen, we could just do, say, percent by volume is supplied here. So we can pick that, and we can say, we have 21% oxygen and 79% nitrogen. Add that. So in other words, notice when I add that, air is composed here. It's shown this graphically here. Properties of oxygen and nitrogen, the mass fraction and the amount of mass we have added are all shown here. Well, let's go. These are all proportional mass, so it doesn't matter what is in here. If you go to the state panel, we have already composed mixture A as combination of oxygen and nitrogen, so that represents air in this case. What we know about the state, 100 kPa. Again, this is a straightforward state calculation. 300 and mass is 10 kg. So notice now, not only we get all the state properties, but all the partial properties are given in this table. What is the partial pressure of oxygen, partial pressure of nitrogen, etc. To find state 2, again, we supply the known properties. We have the same mixture, and temperature is known, mass is equal, and volume is equal to the initial state. So that's enough to find the final state. Again, the final pressure is exactly what we got in the binary mixture, which is what is expected because we didn't really change anything. 1166 kPa, and I bet Q will be closer to this number. We go to the IO panel, so we calculate Q equals mass times change in energy. Everything is same, we're just repeating the calculation, and the answer in the output panel is displayed as 29.8, exactly what we got for the binary mixture. And now comes the equilibrium mixture. This time we're going to first launch the IGE model, NIGE, and this is going to look just like the NIG model, but it's quite different, much more powerful test step. Notice instead of mixture A, mixture B, now we have reactants and products. But look, now you cannot go to products. If you try to select product, it will tell you that you cannot, you first have to define the reactants, obviously. Okay, so let's define the reactants again. We'll go again by, let's say this time we say, okay, percent by volume. We say oxygen is 21% and nitrogen is 79%. Once we add that, the mixture is composed. So there is basically 21 kilomole of oxygen, 79 kilomole of nitrogen in proportion. That's how the mixture is. It's exactly the same mixture. Reactant hasn't changed. But this time we go to the products. And because we are allowing oxygen and nitrogen to react, notice that already the test step picks up the possible candidates. So you can pick and choose. Suppose you want to know what is the biggest constituent, nitric oxide or nitrogen dioxide, or what is produced when oxygen and nitrogen are heated to a very high temperature. Okay, let's select all these components. You could do manually. We don't know their amounts. We just add them to so we don't know the amounts. That's what we want to find by evaluating the state. If we go to the state panel, first we choose the reactants. Again, what we know about the reactants, the pressure is given to us, 100 kPa, and temperature is given to us is 300 Kelvin, and mass is 10 kg. So once again, we found the state of the reactants and the partial properties are supplied in the table. Then we go to state 2, automatically notice the product is selected. So states are kind of keyed to state 1 means reactant, state 2 means products. In this test step, there is no other states, only 2 states are possible. Once again, what do you know about the final state? The pressure is known, temperature is known, 3500 Kelvin. Well, notice that in the IGE model, we can only enter pressure and temperature. Volume is not an option right now. So we have to do a little bit of iteration. We'll guess the pressure, final pressure, and make sure that the volume that we produced is the volume of the tank. Again, I forgot to mention the volume of the tank was 8.648 meter cube. Let me write it down. The volume I should have written down long time ago. How much is the volume? It was calculated to be 8.648. That was obtained from the IG model, or IG plus IG model, or NIG model. Now let's see what IGE model has for us. So we go back to the IGE solution. So for state 2, remember we got something like 1100 something. Okay, so let's enter what we definitely know. 3500 is the temperature. Mass is definitely same, 10 kg. And let's say the pressure, do you think it will be more? Or let's just guess 1200 kPa. Remember the pressure was 1166. So let's try to see what it produces. So this produces a volume of 8.64, and we want a volume of 8.648, a little more volume. Well, we can say, okay, to get a little more volume, the pressure might be a little bit lower. So let's try 1150. Oh, actually if the pressure goes down, volume will go up. So I'm sorry. So the pressure is actually a little bit higher, slightly higher than 1200. So we'll go for 1250, let's say. And you get the idea, 8.29. and what we are after is 8.64, so we got to go a little bit, even a little bit higher. So it produces 7 point. So this is a highly nonlinear calculation, because as you can see, my products are changing as we change the pressure, and as a result, if you be a little bit diligent, you can always find a compromise where the volume will be almost same as the volume of the tank. Then if you come back to the composition panel, you will see that the composition is shown in this graph, and as you can see in this plot, in this pie chart, that NO is the biggest contributor to what is produced as a result of chemical equilibrium. You could say very easily, you can say, okay, let's assume that there is no N2O or this, and suppose you want to remove a few of them and recalculate. You can remove them, and all you have to do is to go to the state panel and calculate again, and this is updated for the new mixture. That is, you can select, pick and choose what you want in your products. Anyway, this is a little bit complicated problem, but in many problems, pressure and temperature are known, and it becomes very simple. You don't have to iterate. But as you can see, I can keep changing P2 and to fine tune. So it's somewhere between 1250 and 1300. Maybe the final pressure is 1275, which might be closer. So if you do a little bit of graphical study, just draw how volume is changing with pressure, you can fine tune the pressure. So let's say we got the volume just right. Now that we know the volume, in the IO panel, we can figure out what is the heat transfer. Q equals M1 times, this formula doesn't change because mass hasn't changed, the new energy. Now this energies reflect the new mixture. Notice it's considerably different, 36.54. So the Q became, so our conclusion is that with IG model, it is something like 1275 kPa, and Q increased to 36.54 million joule.